All right, so now when it comes to combining horizontal transformations, things become a little tricky, okay? As a matter of fact, quite trickier than how it was when we were combining vertical transformations. So let me now move on as small steps as possible to ensure everybody following with this video lesson can have a full understanding. And of course, there are some details explain why it happened that way must be left out. Okay, so I'll just get directly into the practical side where you can, once you learn from the lesson, you should be able to independently work things on your own right there and apply the transformations on your own, the combination of the transformations, of the horizontal transformations on your own. But the theoretical explanation of that we'll have to leave it out for a textbook to write all of that, or you can see with your instructor outside of the course to ask for extra clarifications. Okay. And so now we have seen the combinations of transformations on the vertical axis, or in other words, I call it the vertical transformations. There was a certain order. So back when it was a combination of vertical transformations, then we were doing the stretch, okay, or compress. The vertical scaling is done before the vertical shifts, okay. Surprisingly, when it comes to combining horizontal transformation, we can do it in whichever order we want, and that's where it starts getting tricky right there. We can do the horizontal we can get horizontal shift done first, and then it comes to horizontal scaling in this order. Horizontal shifting coming first, and then horizontal scaling coming after. That's one way. Okay, a little bit out of expectation, a little bit out of what we expected from the preceding learning, because when it was vertical transformations combined together, then we strictly have to stay with that order where the vertical scaling comes before the vertical shifting. But now when we step over to this world of combining horizontal transformations, we can actually go with the shifts first and the scaling comes after. That's one way, but I'm telling you, it's one way. And then on the other hand, or we can still stay with the scaling first, okay, the horizontal, or we can still stick with that rule where we apply the horizontal scaling first, okay, and then we are doing the horizontal shifting after, okay. That's also going to work, okay. But what matters is that we have to know how to express, how to write our expressions correctly so that we can land into the correct way. So now, to make things really consistent in one lecture, allow me for this particular lesson to rule out. So I'm not going to go with this method right here. I'm not going to go with the method to write the expression that, and you will later on understand what expression I mean. But I'm not going to go with the method to show you how we can apply the horizontal shifts before the horizontal scaling, because it's making it a little bit inconsistent with how our mind already been set for after we've learned about vertical transformations combined together, that we were kind of set into that path where we are applying the scaling first and then we are shifting up and down after. So here I'm gonna in this lesson, in this lecture particularly, I'm gonna show the method where we can apply the horizontal scaling first to make it really consistent and light and very similar to the way how we did that combinations with the vertical transformations. So we're going to apply the horizontal scaling first, and then we're going to do the horizontal shifting after, and then we're still going to produce the same result. Okay, so now that's the plan for here. I'm not going to show, in this lesson, I'm not going to show, so if anyone would like to see the extra lesson here for this particular approach here, then maybe you can wait for another video lesson separately, okay? But that's not something that critically required for any pre-calculus course right there, okay? So now as the tentative plan right now, as a tentative Friend, we want to stick with that routine where we apply with that rule, where we apply horizontal scaling first and then horizontal shift after, okay, to make it really consistent with how we're doing that combination when it was for all the vertical transformations. Okay, so now that's one thing I need to be clear with everyone. And so now getting into it, so we understand that, we already understood quite well that, let's say, and now I can even just erase this to maximize our board space right here. And so we're going to start out, and in this approach, allow me to approach directly with a graph that's already given. So I'm going to really do one example, even though I don't formally name that example, but I need an example for you to see what's going on. Okay, so here we're going to actually work. I'm going to explain side by side with an example being presented. So we're going to have a function f of x being represented as a graph. Okay, be in the graph. All right, so in that way, now allow me to pop out the graph right here. This is the graph, and let it now be at the corner of our the board here, of our viewing window here. So there's the graph. So that's the graph for f of x being being printed in red color right here. And so yes, we call it, it's a parent function or whatsoever. It's a parent function. Okay, so we have already learned through the earlier lecture when I was going over all the elementary transformations on each one of the elementary transformations. Then f of, just simply f of an x, and then let me pick a number, okay? F of x minus 2, for example, okay? F of x minus 2. Well, so we've learned earlier in that earlier lesson that we strictly want to always bring that into the minus form. So if we had an x plus 2 here, but if we have a problem like an x plus 2, then we purposely want to write it as an x minus negative 2. Okay, so in my style of teaching, I would like my students to express that x minus, because that will bring about the horizontal shifting. Okay, and then whatever number here comes after the subtraction will be the amount being shifted either to the left or either to the right. Okay, so an expression like this is indicating we're going to shift this particular function with the graph here to the right hand side by how far? 2 units far. Okay, so let's double check with the result here. And so now, according to the result, all right, so let's show it. This is now the graph in blue. Okay, and now I'm going to quickly put it in close zoom full screen view for anyone to see. And then I can also put in the guiding points again, and we've learned all of these terms from previous lectures right here. Okay, so these are all the guiding points. So if we compare the guiding points side by side, and every single point is being shifted 2 units to the right hand side, being shifted 2 units to the right hand side. That's just a brief review of what we're doing. So just a recall that doing this is gonna bring it to the right. It's gonna, okay, so as an explanation, this arrow means to be shifted, okay, shifted to the right hand side by 2 units. All right, and then of course I've been sharing with that advice about, we add 2 to every x value. Yes, that is true. That's the case here. That's why we're seeing the graph is being pushed to the right hand side. Okay, and so I'm using here just for the short explanation purpose, allow me to use shorthand writing. So shift to the right. That's why I'm drawing this arrow pointed to the right by 2 units. Okay, and then if we are doing this, okay, and now I'm gonna put the graph away. Just stay only with the original parent function. So if we're doing for example, a 2x right here. Okay, if we're doing a 2x, then yes, this means now the value here is positive. Okay, and then we've learned that if the absolute value of this coefficient And by the way, in the form of a coefficient multiplied with x, a coefficient other than 1 multiplied with x is going to give a horizontal scaling, okay? Either a compression or a stretch or even a flip, okay? And so in that way here, for this particular problem, I'm expecting that the expectation here is that we're going to have a compression, okay? It's compressed, and to be precise, it's horizontally compressed. All right, horizontally compressed by a factor of 1/2, and that what it means is, everything is going to be halfway down. Okay, that's a scaling factor right here. Okay, so now here's the idea, but this is just easy from the earlier expression. What we want to do now, this is where things get combined right here. You will be asked to do the following. Okay, how about a 2x minus 2, for example? And this is sadly the way how most of the time the expression is expressed. It's if we look a little more closely, okay, this is in the form of a linear, okay, this is in the form of a linear, that's famous linear mx plus b form, okay, or how about I can just write it as a linear ax plus b form, or you can just say it's a linear form, okay, without worrying about ax plus b, because it's a little counterintuitive in a sense that here it's a minus, but generally a linear form is an ax plus b. Okay, so all you have to keep in mind is very commonly you are given a function, okay, I mean a function that's defined by, and of course this is a descendant function, g of x, for example. So some descendant function is defined as the parent function, but substituted in, but taking the expression as, taking this linear expression. That's why I call it, it's a linear form right there. It's taking a linear expression. And then, so it has that 2 like this, but it has that minus 2 like this one. And that's the reason why I brought up these two first. So here's the dangerous thing. And now I realize it's kind of hidden behind my graph. So I'm going to turn the graph away. So here comes the dangerous part. So at first sight, looking at something like this, okay? At first sight, looking at something like this. And let's move over here to this board right here. So now once again, when we're looking at this, g of x as a descendant function defined to be a f of 2x minus 2, okay? That parent function is taking the expression input. So back to what I was saying earlier, at first sight, it makes us think, and again, we want to keep ourselves in that rule that we're going to do scaling first, okay, horizontal scaling first, and then the shifting after as step number 2, as the second step, as the step after. And so in that way, it makes perfect sense that we're looking immediately into this. Okay, it makes perfect sense that we're looking immediately into this. And then we think that, so there's going to be, and of course, now with the graph being brought up, okay, we can, and I also purposely put all of the guiding points here for this graph. Okay, so this is what will make us think as following. So on the set of guiding points, the parent's function had minus 3, comma 3, okay, and then we had negative 1, comma 1, we had 1, comma 3, we had 5, comma 1, and we had 8, comma 6, and we had 11, comma 1, okay. So these are the guiding points of right there, that stays right there on our graph. That's making it easy. But back to what I was saying. So now as a step, as a multi-step transformation work here, And like I said earlier, we want to stay in that rule where we want to do the horizontal scaling first before the shifting. And so we think about, yes, producing f of 2x. And so just like that advice I gave out in the earlier lecture, then to properly produce our transformation here, then every point from every guiding point here, every guiding point before the transformation, we're gonna just simply multiply each x value by a factor of 1/2, because this is 2 here, so we multiply by a factor of 1/2. So this gives me -3/2, comma 3, okay? And then this point here gives me a -1/2, comma 1. This point will give me a +1/2, comma 3. So everything we are doing here is only happening on the x values, okay? And then so 5/2, comma 1, and that's here giving me 4, comma 6, and this here gives me 11, gives me 11/2, comma 1. All right, so but that's not our completion point, because we need one more step that shows when we subtract 2 from the 2x right here inside the parentheses of our parents function. So here that rings a perfect bell that we're not done yet. Okay, and so after this point, and as I said, starting out with that transformation, by doing this horizontal scaling first, and that's what we're expecting, and things go just right, just like how things has been. Okay, and then when we get into the next step where we're putting in that additional element -2 from 2x inside of our parentheses, okay, f of 2x minus 2, we are going to think as following. We're going to think about adding 2, well, just like how I was showing it before. I mean, almost like how I was showing that before. We just think about, we will naturally, I'm saying as just a natural mind process, I mean thought process, and we naturally going to think just like from what we've learned from the earlier lecture, that we're going to add 2 because it's a minus already. Okay, so we're going to add 2 from the preceding step. We're going to add 2 to every y value. That's what we naturally think. Okay, then let's do it that way. So that means if we're doing it that way, add 2 because of this value right here. Add 2 to, because mainly I see a minus sign, so it's already in a form of, it rings a bell about shifting it to the right hand side. Yes, I agree. But then this 2 right here, being a positive 2, meaning we're going to add 2 to every current x values of our currently transformed version of these guiding points. Okay, so let's do it that way. And now, so 2 added to a -3/2, okay, gives me a positive 1/2, and that's comma 3. So nothing is done to the y value at all. Only everything now is only things that happen on the x values. I just now added 2 to -3/2. Okay, and now I add 2 to -1/2. Okay, which will give me positive 3/2. Okay, comma 1. And then so for the next point here, I am looking at positive 5/2, comma 3. And so provided that you are already fluent with adding and subtracting fractions and by making common denominators and all that. Okay, so now 5/2 plus 2. Okay, that will give me 5/2 plus 2 will give me 9/2, comma 1. Okay, and that's the transform point as the next step after this one. Okay, and then I'm moving on to here. This is so now 1/4, but I'm going to add 2. I mean 4, comma 6. I'm going to add 2. So 4 plus 2, it's going to give me 6, comma 6. So these are the guiding points right here. And then now 11/2. Okay, 11/2. I'm going to add 2. All right, that gives me 15/2, comma 1. So this is the next step, the transform point as the next step right after the step. So we believe we're done. We believe we have arrived at the correct the positions, the correct final position for those guiding points, and then from here we are going to complete the graph. Okay, so now I'm going to use the computer to really quickly get the graph of this, and I'm going to put the guiding points in, and then we're going to find out. Okay. All right, so now on with my graph in full screen view right here. Okay, so let's look at the following. All right, so now I'm going to first put in the guiding points. Okay, with the labels. And I'm going to zoom it in. All right. And I can still zoom in a little further, so that now when I put it in the corner of my board right here, we can start comparing already. Okay, the first point here, all right, happens at, based on our calculation, the first point should land at 1/2, 3. Okay, look at what's going on with the first transform point. It happens right at negative 1/2, 3. Wait a minute. We did not do anything off with the calculation. Okay, and then consistently, if we keep looking further in the other points right there. All right, so now, again, the next point. So we noticed the first point was already off. Off. Okay, and then the next point, based on our calculation and assuming we're doing everything without mathematical error, okay, so we should be at 3/2, 1. Okay, let's look at our second point from the left to the right right there. We already knocked down that, hey, our first one here is already off. But let's compare the second guiding points in blue on the graph that's present there with this one right here. All right, it's here. The label shows a positive 0.5, meaning a positive 1/2, 1. It's off again. It's off again. But here's the thing. It looks something consistent because so now, again, in closer view right here, the space between these 2 points, the amount of change in these 2 points from minus 0.5 to positive 0.5 is exactly a 1 square unit. Okay, so at least something on the bright side here. The space between 3/2 and 1/2 is also exactly a 1 space grid right there. So something consistently off throughout all of these points compared to the version we are seeing on a graph. That's what I'm trying to point out right here. So now I got to be even more clear here. So this one here, we're off by, okay, by 1. And here we're also off, okay, by 1. We're off again, and off by 1. Okay, this point here, the way how we calculate it is off by 1 in a sense that this point is supposed to be 1 square grid further than the one that's showing on the graph. And this is computer I'm talking about. I typed directly this formula, okay, this setting into my decimals here, and this is what we calculated. So something must have gone wrong. Okay, something must have gone wrong. All right, so let's check again for these points right here. And now you can spend your time checking, and I can still leave the graph there. Okay. And now let's put the graph in even closer zoom. So assuming that you have already had your guiding point copy down right there, then these are all the points that they're all completely off. Okay, they're all being off by 1 point away. Okay, so the third point here, our calculation showed 5/2, 3. So 3 is here. Okay, 3 is here, but this point is 1.5, which is a 3/2, 3. That's the label it's showing right here. We're off by 1 again. Okay, we're off by 1 again. Okay, so this point here is 1 square. Our calculated point should have made it landed here, but now it's here. Okay, we're off by 1. And then the same with this point. And the same with this point. So every point we're off by 1. So what is going on here? What is going on here? Okay, we're trying to find out what is going on with this. So what we have done, not correctly here. Okay, so something must have been incorrectly done here. So now here's the idea. And if we don't believe our technology that we're currently using, then we can switch to a different one. You can type directly this inputs. Okay, you can use a TI calculator. I use decimals. For once I thought decimals was wrong. Okay, and then I checked that with the TI calculator. It shows the same exact graph as the graph you're seeing on the screen right here. Okay, but it's still off exactly like by 1. Okay, from our table. Okay, and then I use other advanced software. It's still showing the exact result as you're seeing with the graph here, but our table is off. All right, so here's the truth behind the scene. Here's the truth behind the scene. All right, so now, so we still want, so when we're doing this, we still want to do horizontal scaling first and then doing the shifting. So in this expression, if we are doing it by hand, if we're doing it by manual calculation, by the actual calculation, step by step, then this is what we need to do. Okay, so now I'm going to update this. Okay, so that was wrong. We noticed how wrong that was, so there's no reason to keep it. Okay, so now if we're looking back at that expression here one more time, we know enough math. We know enough math to do the following. Okay, we can see this 2x minus 2, and we can, you see, we can see this as a, we can see this expression here as a factor in the factor form. So if I factor out that common factor 2, now be careful. In this case, this 2 right here has a common factor with that. But in the worst case where it's not even having a common factor, you can still purposely factor out that lead coefficient here. So I call this 2 the lead coefficient. Okay? And now I'm talking about in the worst scenario where you don't even have a common factor here. Here we do. It's a 2 and there's a common factor 2. So factoring out, it's 2 in parentheses x minus 1. Okay? 2 in parentheses x minus 1. Then so, and like I said earlier, even if in the case where you had like a 2x minus 5, for example, and then you would, and after factoring out the 2, we're going to end up with x minus 5 halves. Okay? But basically, we're experimenting right now. We want to find out what's happening if we factor out the 2. Factor out the 2. So in this current expression, so again, usually we are given a problem, or we are running into a problem where the parent function takes a linear expression like this. But then right now we're exploring the case where what if we factor out that lead coefficient, the part inside the parent function. Okay, what if we factor out that part? So factoring that out, we're ending up with the 2 times in parentheses is x minus 1. 2 times in parentheses is x minus 1. So think about it this way. So now seeing that 1 and allow me to underline that 1 right here. Allow me to underline that 1. It's x minus, so it rings a bell about shifting to the horizontal shifting. It rings a sign, it rings a bell about horizontal shifting. Here clearly it was these points, but now x minus 1 here. Why don't we look at things like this? Okay, this means I'm gonna shift all of the points here 1 unit to the right hand side. Only 1 unit to the right hand side. Or in other words, I'm only going to add 1 to every x value of the previous step, of the very preceding step. Okay, so in that way, here's how I'm seeing it. So earlier we were adding 2 to every x value of the preceding step, but now we only, in this form of seeing it, I'm more firm that let's add only 1. Okay. And so now 1 plus with minus 3 halves. That gives me minus 1 half, comma 3. All right, minus 1 half, comma 3. minus 1/2 over 3. And that is the first point of our final guiding point. And now it lands right here in the first point right there. Looks pretty okay so far. But let's check for the rest of them. So now on the next step, so once again, so I'm adding 1 to each point right here. So now we're going to find out. And I should have used black ink here and blue ink for the writing. So for this point, I'm going to add 1 to negative 1/2. So negative 1/2 here plus 1, I'm going to have a positive 1/2 and comma 1 for the y value. And again, it looks consistent and it looks correct with the second point in blue still being presented there in the graph. Okay, in the graphing space right there. Okay, and then let's advance even further. So how about 1/2 plus 1 plus 1? All right, and so now 1/2 plus 1 gives me a positive 3/2, and now the y value, comma 3. This point, the third point on our list, is also consistent. It's also correct with the points being presented on the graph. From the left to the right, first point, second point, third point. Okay, the coordinates is here in blue. The coordinate label is here, 1.5 comma 3, which tells me that it's 3/2, positive 3/2, positive 3/2 comma 3. Okay, so now we have 3 points by doing this. Add 1 right here from the preceding step. We've had the 3 points correctly done so far. So let's look at the next one. So 5/2 add 1, which will give me 7/2, comma 1. And that point, once again, looks correct with the point that's generated by my graphing device. This point right here, adding 1 gives me simply just 5, comma 6. And again, we do have that second one from the last point compared to the graph being correct as well. Okay, and so it's yes, it's 5, comma 6 right there. All right, and so now the next one I'm looking at 11/2 plus 1, 11/2 plus 1. So that gives me in parentheses 13/2. Okay, 13 over 2, comma 1. Okay, and so now all of these points fit perfectly on the correct spots right there, from what Desmos give, from what any the technology, the graphing devices give. Okay, and now we're going to go ahead and draw the graph over. All right, so in full screen view, this is what the graph looks like. All right, and that's the graph. Okay. So now learning from that lesson, the bottom line I would like to point out now is that in order to achieve the correct results when we stay with that rule, so the rule I previously defined, that I previously led you into that rule, we stay with doing horizontal scaling first and then doing the horizontal shift after. So if we stay in that rule, then anytime you are presented, anytime you are given a problem like this where it's the parent function, okay, but then taking the input as a linear expression inside of that, I call this a linear expression inside of that, then to land into the correct results, to land into the actual correct results, as we just now verified, then we need to factor out, so looking at this form here directly is not going to tell you the true story. Even though I understand very commonly and big amount of times you are given an expression like this, where the entire linear expression is given. Not very commonly that you are given in factor form, but here you are given in the foiled out linear expression like this, as an expression, as the input expression of a parent function. Okay, so in that case, and along with what we want to do, apply the horizontal scaling first or before the horizontal shifting, then we must, the one critical step that we must take is to factor out to factor out the leading coefficient here in the linear expression. So in other words, now just looking directly at this is not telling you the correct answer. It's not telling you the correct setting. So in order to get your correct result, in order to achieve your correct result, we need to, so that important step you have already seen, we need to factor out this factor right here. So this factor right now, I mean this coefficient appears right now, it's a 2. Okay, it's a 2. So I'm going to factor out a 2. And so in this particular problem, we have a common factor. So it's going to be x minus 1 right here. Okay, so now put that linear expression as the input of our parent function. Put that linear expression in a factor form. That will guarantee our work land into the correct result. Okay, so this here explains this 2 after factor out explains for just like that first step. We will multiply every x value from the preceding step by a factor of 1/2, and that's how I generated these. So even in case that leading coefficient here was a negative, just factor the coefficient with the negative sign, and we will get that through the examples later on that are common. Okay, and then so here I just like a 2x step right here. Okay, then I multiply every x value with the 1/2. Okay, and that's how I produce this. And then in the next step, just think about I only replace the x by x minus 1. That rings a bell that we need to add only 1. Okay, to each x value, each of the x values of the preceding step. And that's how this is the correct one, and that agrees with the result generated by any of the graphing device. Okay, and if we are directly doing this, okay, with the paper and pencil by constructing table of values, it will land into this result as well. Okay, so again, in this case where I want to first take the horizontal scaling first and then do the horizontal shifting after, then we have to factor out the leading coefficient. So one more time, I'm saying it out loud clearly here. Then we want to say, first of all, I already led you into that way, and allow me to, in this lecture that I completely ignored about going with the opposite way around, that doing the horizontal shifting before the horizontal scaling. That you can find me, if you're a student who is learning directly with me, you can find me either through some given contact through the school, or you can wait for some future video where I explain that outside of the required course content. But here I formally teach that we stay with that rule where we apply the horizontal scaling before horizontal shifts. Okay, and so in that way, now once we set ourselves in that rule, then we have to always factor out that leading coefficient, that lead coefficient of the linear expression, okay, inside our parent function. All right, and that is the reason why now after factoring out, see, I had a 2 here. Okay, and so now after all of that explanation, then we are ready to head into a formal example. Okay. All right, so you already have seen some action. So allow me to start putting in some examples here. And the example problems are going to be quite similar to what I have demonstrated through that demo example earlier. So now I'm going to call this example number 3. Okay, and I'm going to say let f of x, okay, let f of x be represented, okay, by the given graph. Okay. All right, so let's show that graph. That is the graph. Okay, let f of x be represented by the given graph. So once again, and this was also the same. This is also the same graph that I used in that demo, the example. Okay, in that example where I was illustrating the idea. So it's such a nice looking graph, I decided to use it again. Okay, So now whatever function is, there has to be a rule already. There must have been a rule. It's just we don't have to specifically know that rule. But that rule for f of x has already been represented as the graph here. Okay, so we're treating f here as a parent function. And so now we want to sketch. All right, sketch the graph of the following function. All right. And so now I'm going to call that part A. And so here in the entire example 3, it's all about you're going to be given different descendant functions. Okay, and any of those is going to be related with f of x somehow. So let's look at g of x defined as, how about the function f of x, but it's taking negative 1/2 x, negative 1/2 x plus 1. Negative 1/2 x plus 1. Okay, and so this is the linear expression that I was talking about throughout that illustration or that demo example I was doing earlier. This is that linear expression. All right, that is what I'm talking about. There's a coefficient in front of the x term, and then no parentheses or anything like that, and then plus 1. So it's in that ax plus b form right there. Okay, it's in that ax plus b form. So it's, in other words, or generally speaking, I see this as a linear expression. Okay, but so now, clearly speaking, a problem like this is going to involve two horizontal transformations together. Okay, or because I see a coefficient other than 1 here, so definitely it's going to have to do some scaling horizontally. Okay, it could be stretch, it could be a compression, it could be a stretch. Okay, and then we're going to have to shift because there's that. See, and by the way, so this is what, minus 1, I mean plus 1, so it looks like it's going to be a minus a negative 1. But we're going to hold on to all that because right now a lot of things are still being unclear. All I wanted to point out is that what we have here is a linear expression. So I am expecting this is a combination of two horizontal transformations together. Okay, and then as we already set a clear rule for ourselves among me and students who are learning with me, that let's just stay with that rule to be consistent with the earlier lesson we've learned, that I just want to do scaling before shifting. So horizontal scale, I'm going to do horizontal scaling before shifting. Okay, so in order to do that successfully, by taking the correct horizontal scaling before the shifting, then we have to do the following. So now we need to do some algebra. Okay, the formal work now is that I am going to turn. So just like what I said earlier, we need to focus right at that lead coefficient. So this time, and we will always include the negative sign. If there is any negative sign, include the negative sign with the lead coefficient. So in this case, the way how I see it, the lead coefficient is negative 1/2. The lead coefficient is negative 1/2. All right, so now in that way, we want to factor out the entire negative 1/2 lead coefficient now. So that means in my next step, I would like to write, I'm looking for a way to write my function here as f of, but now the two terms minus 1/2 x plus 1, I'm going to factor out negative 1/2. So start thinking about what's going to be left behind inside the parentheses here. And this is where all of your algebra background from the previous course will come in again. Okay, because all of that understanding you've learned in your previous courses, including the factoring skills, will count significantly in this particular problem. So allow me not to mention too much of that. That's whatever you have learned from prerequisite courses. But factoring out a negative 1/2 right here, you will end up with, well, x. For the first term, since you pulled away negative 1/2, then of course what's left in parentheses here is just x as the remaining factor. But now think about with this plus 1 right here, this term right here, being a positive 1. But if we divide away negative 1/2 because we pulled it outside the parentheses, then it becomes negative actually, minus. And then negative So minus 2 indeed. Okay. And how can you, so for viewers who are following with this, you can go ahead and pause the video and do the following to check my factoring work. And that's also your own trick for you. That's also your own hint for you to check, to double check against yourself like that. Pause the video and do this. Multiply that back and multiply that back. Okay, so negative 1/2 times x. And then negative 1/2 times negative 2. Pause the video and do that. All right, so now I hope that anyone, once you have resumed the video here, you already double checked, and this is exactly the factor form of our starting minus 1/2 x plus 1. Or in other words, we have successfully and correctly factored out this. Now that tells the story. Now this factor form of our linear expression from the start, this factor form will tell the true story. Okay, we will use this factor first for the scaling, the horizontal scaling. And then once we're done with the scaling successfully as one step nailed down, we're going to apply the shifting by this amount. So this is the true value that's responsible for the shifting. Okay, in case I didn't explain it that way when I was talking about it earlier, now I can double confirm that. This is the true value that's responsible for how much we're shifting. Okay, if we're doing scaling, horizontal scaling first, and then horizontal shifting after. All right, so now in that way, we are now ready for constructing the table. So the reason I reuse the graph here is because I already had the table constructed on the other side of my board, and I don't want to erase everything out and completely and construct a brand new table, so allow me to use the same graph right here. But we still learn the generality out of that. Okay. All right, so now on this table, on this board right here, I want to erase the big part of our table here. So g of x really was f of minus 1/2 in product with x minus 2. All right. So now, as I said earlier, we are going to use this coefficient here, this factor right here, to determine how much horizontal scaling we're going to have, and we're going to use that value here to be the one responsible for the horizontal scaling, and we will be doing horizontal scaling first. Okay, so that means the next step in my table here, and provided I already sketched down all of these guiding points, then the next step comes out as following. I'm going to construct a column where I apply the transformation where it's negative 1/2 x. And this is now even more clear that, see, this is in this column right here, it's only a horizontal scaling, okay? Because in that form of a times x right there. Okay, and a couple of expectations we can already have in mind before we started. It's a negative a, so I do expect a flipped around, through the y-axis, and then we're gonna have a stretch, okay? Because absolute value of negative 1/2 is less than 1, so we're gonna expect a stretch. Okay, but in the end, with all of that, let's take that advice that was famously given in the earlier lecture. All we have to do is multiply every x value among the guiding points here by the factor of negative 1/2. That's why it's extremely beneficial that we factor out whatever the leading coefficient from our linear expression, and that will tell the true story. Okay, so now negative 1/2 times negative 3. So this point here, negative 3 comma 3, is now transformed to positive 3/2 comma 3. Nothing's done with the y value. Okay, and now for the next point, negative 1/2 times negative 1. And the point here originally on the parent function was negative 1 comma 1. So now it becomes a positive 1/2 comma 1. Transform into positive 1/2 comma 1. Okay, and now for the next one, 1 comma 3 is that guiding point on the parent function. You're still seeing that here on the graph. Okay, And now I'm going to multiply x value with negative 1/2. So negative 1/2 times 1 is a negative 1/2. Okay, comma 3. So now that point 1, comma 3 is now transformed to negative 1/2, comma 3. The next point here, okay, is transformed into negative 5/2, comma 1. And now I can start picking up the pace a little bit right there. Okay, and then with this one here, it's going to give me negative 4, comma 6. All right, and then the last point here is transformed into, so now negative 11 over 2, comma 1. So these are our guiding points after applying the first step. And the first step was, again, the horizontal scaling. That's what it is here. All right, and now in that way, we are ready for the next step where we're going to apply the horizontal shifting. Okay, and so now, so the next step, I'm going to produce the result for f of, so minus 1/2 times x minus 2. Okay, I'm going to produce the result of the transform points after we, so this 2 right here is what's going to determine how much to shift, okay, and where to shift. So see, now we're in that famous form x minus x subtract, so that rings a bell that we're going to do a horizontal shifting. And furthermore, we have a positive 2 now after that subtraction. That's to be consistent in my style of teaching this. And so now in this case, I see we're going to shift to the right hand side because it's actually positive 2. After isolating out the x subtract, okay, then just after x subtract 2, positive 2. So we're going to shift to the right, okay, but by how far? By 2 units, okay, from whatever we have done here. All right, so now we have a clear direction. So now 3/2, I'm going to add 2. So stay with that advice again, okay? Anytime we're doing a horizontal shifting, we want to add that value. It could be a negative value in other problem, okay? So after we have already exhibit that nature here, it's a minus, right? And here I'm looking at adding 2 to every x value of the very preceding step right there. Okay, so now 3/2 plus 2. 3/2 plus 2 is going to give me 7/2. All right, 1/2 plus 2 is going to give me a 5/2. Okay, and comma 1. Negative 1/2 plus 2 is going to give me a positive 3/2. And comma 3 for the y value. Minus 5/2 plus 2 is going to give me a negative 1/2. And comma 1. All right. Negative 4 plus 2 is going to give me a negative 2 with comma 6. All right. And now negative 11/2 plus 2. Okay. It gives me negative 7/2, comma 1. And allow me a minute or so to double check my calculation quickly here because I was doing that in a rush. Okay, that's adding with 2. Okay. All right, and so now let's bring these points on the graph. Okay. All right, so now with our graph in full screen view right here. All right, I am going to put in the guiding points first. All right, so these are our guiding points. Okay, these are our guiding points. And I need to zoom it out a little further so that I can see all the points. Okay. So now recall that we had a flip because of this negative coefficient. That's explained that we had a flip of reflection through the y-axis. So in that way, I do expect that this graph right here, you see in our parent function, the first from the left to the right, our parent function has this bow that's pointing down. Okay, this bottom half of a bow, and then there's a straight segment, and then there's a line zigzagging up and down. Okay, but now being in a flip version through the y-axis here, then I'm expecting from the right to the left, the bow is here, the bow part is here. Okay, and then these points are all here, where line connecting down and line connecting up and zigzagging down right here. But now comparing okay, so now I'm gonna get my table ready for the sequence of the transformation steps. All right, so in the very next column here, I am going to calculate how f of negative 1/2 x will transform all of these guiding points. Okay, so remember that advice I've had earlier when we learned about this. With this coefficient, a could be negative, could be positive, could be whatever, and an absolute value being less than 1 or absolute value being greater than 1, all we do is to break it down into one advice right here. We are going to multiply every x value from the preceding list here by 1 over. So we're going to multiply by 1 over a here, which is in this case 1 over a negative 1/2. Okay, or mathematically negative 2. So that means we are going to multiply negative 2, even though see, the a value itself here is a negative 1/2. I emphasize that. Okay, so we're going to multiply negative 2 to every x value, okay, of the parent function. And so we just simply need to focus on these guiding points. So that means in the next step, my first point here is transformed into, so negative 2 times negative 3 gives me a positive 6, okay, and comma 3. So nothing happened to the y value, only the transformation applied to the x value right there. Okay, so now in the next step, I have negative 1 times negative 2, which will consequently give me a positive 2 and comma 1. So that point negative 1 comma 1 on the original parent function is now transformed into 2 comma 1. Okay, and then the next point we're having 1 comma 3. So 1, the x value will be multiplied with negative 2. Okay, and it will give me consequently negative 2 comma 3. All right, and we will have 5 multiplied with negative 2, so that our next point, in our next point right here, 5 comma 1 is transformed into negative 10 comma 1. And again, throughout the whole work so far, nothing happens to the y values. Nothing is done on the y values. Okay, and then 8 comma 6 will now transform into negative 16 comma 6. And then now I can really pick up the pace right here. 11 times negative 2 gives me negative 22. Okay, and comma 1. So these are all the transform points right here. After multiplying every x value here by 1 over a. 1 over a. So mathematically, in this case right here, it's a negative 2. Okay, and then in that way, so now we are ready for the next step. The next step now is to horizontally shift. Okay, and so now with our expression initially was a linear expression, but now factors, right? Now in factor form, we already exhibit that nature that it's an x subtract, and so this value here will be the one responsible for the horizontal shifting. It tells us how far we shift and where we shift. Is it to the left or to the right, or to the right or to the left? Okay, so in this way, now we have already learned that from that lecture where I was introducing the elementary transformations. Then here we could just gonna, after we have already expressed our expression here, we have already put our expression here in the form of x subtract. Then that value here we're gonna add to every x value of the very preceding step. Okay, in the transformation. And so that means, so now I'm producing this column to show the transformation after we applied x minus 2, okay? And so now I'm going to add 2 to every x value of the preceding step. So now 6 plus 2 gives me 8, okay, comma 3. All right. 2 comma 1, so 2 plus 2, 2 plus 2, okay, gives me 4 comma 1. All right, and then minus 2 plus 2 gives me 0 comma 3. So that point minus 2 comma 3 is transformed into 0 comma 3. And now I can really pick up the pace right here. So negative 10, okay, comma 1. So negative 10 will add 2. So that gives me negative 8 comma 1. All right, and then negative 16 plus, comma 6 will be transformed into negative 14 comma 6. Nothing's done with the y value. Now the x value is added to. Okay, and then for the last one here, we're looking at negative 22 comma 1 is transformed into negative 20 comma 1. All right, and that now, so that came out after negative 22 plus 2. Now this is our final list of all the guiding points again. All the transformed guiding points after 2 steps of the transformations. Okay, and so now we are ready to see the actual one. Now we are ready to see the real, how we can put these on the graph and draw the graph from there. Okay. All right, now with our graph, the parents function here, with our graph of the parents function in full screen view right here. Now I am going to put in the guiding points. Okay, and these are the guiding points. Okay, and I just now realized they are quite spaced out. So I'm going to have to do a far zoom right here. All right, so now it has all of our points. Okay, so I need to clarify a couple things. So I did explain earlier that there was due to having a negative coefficient here, we would expect a flip. And so now looking back at our graph, okay, looking back at our graph, the graph of the parents function in red here from the left to the right, it started out first being the bottom half of this bow right here, and then it's a line straight down and then zigzagging up and down. Okay, so that's the anatomy of our parents function from the left to the right. So now think about in the flipped version, the version that we flipped after we flipped horizontally, then it's going to have from the left to the right, it has to be zigzagging up and down, and then that line, and then the bow is the last part. Everything is opposite in the horizontal way. Okay, and then through these guiding points, we're gonna be able to draw that even more precisely. All right, so now I'm gonna put the graph back in full screen view, and now we're gonna so that means with all these points and with all these the 6 guiding points right here, I'm expecting a zigzagging up and down and another line here, but then through these 3 points, I'm gonna expect a bottom half of a bow right here. Okay, so now let's see how we can sketch through it. And so now, all right, so that's the first part right there, just like that. If we were really sketching on paper or pencil, that's how it looks. We're going to connect from the left to the right, but as a straight line, as opposite to this piece of straight line right here. And then we're going to continue connecting down to the next point right here as a straight line again, because here it's a straight line. Okay, from the right to the left. So everything here is going backward. Okay, and then continuing from this point to that next point, it's another straight line. Okay, so we have a straight line. But then through these three points, so if we really have to do a hand sketch, then it's just we try our best to make a bottom part of a bow right there. Okay, and that's how we're getting our graph of the parents function being transformed into this blue descendants function right there. All right, so let's now look at part B of the example. So how about we want to sketch the descendant function g of x as f of negative 1/2 x minus 3/2. Okay, so f of negative 1/2 x minus 3/2. Okay, and so now for this problem, before we get started, and of course the graph is still the same parent function f of x here. Okay, so before we started, so just in that experience we have already picked up from the earlier part A and also throughout my detailed explanations before we got into this example, we want to factor out this leading coefficient. And so the sign here is, again, it's a negative sign, and I really want to emphasize this. If whatever sign that belongs to this leading coefficient here, okay, we're gonna factor out that complete coefficient with the sign. And so according to that, and then according to the way how we factor, things will come out accordingly. So now here's how I want to see my parent function with this linear expression as. So it's f, and now factoring out the negative 1/2. I'm looking at negative 1/2 in parentheses. All right, and so now as we factor out negative 1/2, the first term here becomes x, but the second term here becomes just plus 3. All right, it's a plus 3. And so now in this way, I'm seeing this as plus 3. I see this as the same as minus negative 3. All right, and so that means here we have a shifting sideways, a horizontal shifting, because it brings up x minus x subtraction. Okay, x subtract, but then we're subtracting a negative 3. Okay, and so we will put all that details together. So I am expecting, so at this point I'm pointing out there's this value that's responsible for horizontal. Okay, we're gonna run into some horizontal scaling. Okay, and expectedly flipped as well, and flip. Okay, there's some flip, and then this value right here is responsible for the horizontal shift. Okay, horizontal shift. All right, so we will have two transformations being expected here. All right, so now at this point, once we have picked up the pace a little bit, then I'm going to erase this board right here. This board we have. And I don't think I have to erase the entire complete table here, because we can, it's the same graph we're doing. So we can just keep that. All right. And so the function g of x we're looking at now is f of, so minus 1/2 times x minus negative 3. All right, so let's put it in that way. So really it was from the other board in my explanation, it was minus 1/2 in parentheses is x plus 3. But now I purposely want to write the plus 3 as x minus a negative 3. Okay, so now all the transformation is here. We're seeing all that here. So now in this way, then it's just consistent with what I was teaching earlier. We want to do the horizontal scaling first. So now in that way, I am in my table. I am about to create a step, one column that reflects the step where we're gonna apply the horizontal scaling. So this step here is what I would call it that. So if this is f of x, this is the column for the parent function, then this is going to be the column for f of minus 1/2 x. Okay, and so once again, this is in the form of f of an input ax. Okay, f of an input ax. And so now I recognize that a is a negative 1/2, and as I already pointed out from the other board. And so eventually we're gonna get to this. But so 1 over a. That means 1 over a will be 1 divided by negative 1/2. That is negative 2. Okay, so in that way, So in that way, now I'm looking at my transform point right here. So the first, so again, the point now is that when we're in this form of f of ax right here, then the advice I showed in the earlier lecture about, you know, these elementary transformations, any of these elementary transformations, then all we have to do is just at every point, or for every point on the graph right here, we just simply have to multiply the x value. We multiply every x value by 1 over a, without worrying about the sign, because whatever sign that comes with it, it will produce the results for us as we expected. Okay, and so in that way, that's why in that way now the first point here is transformed into, so -3, comma 3, the y value stays the same, but now this becomes a +6. Okay, +6, simply because -3 was the x value, and now we multiply with 1 over a, which is -2 here as well. Okay, and then here again we're looking at -1 comma 1. That was the parent's point, the guiding point on the parent's function, and now it's going to transform into a 2 comma 1. Okay, 2 comma 1, because the 1 value stays the same, and -1 times -2 will give me a +2. Okay, and so now I can start picking up the pace here a little bit. This next point here, 1 comma 3, is transformed into -2 comma 3. Okay, and then so on. This 5 comma 1 is transformed into -10 comma 1. Nothing is done to the y value. Again, I emphasize that when we're working on anything that's about the horizontal, then nothing is done with the y value. And then we're now looking at so 8 comma 6 is transformed into -16 comma 6. Okay, and then this last point here on our list of the guiding points, and here we're looking at -22 comma 1. -22 comma 1. All right, and this is because, again, 11 times -2. All right, so this is where we're done with the first step, but the first step didn't get us to that complete function here of g of x, because this is only f at -1/2 x. Okay, and so now we're going to advance to the next step. So just like how I was explaining earlier in this lecture here, when it comes to combining horizontal transformations, we want to, even though there's another way, but I want to specifically show my students that we want to apply the horizontal, the scaling first, and then we're gonna do the horizontal shifting after. Okay, as the next step. So now in my next column here, I'm gonna write f of, now in brackets here, I'm looking at -1/2 times, and now in parentheses, x minus -3 in close parentheses. All right, so now we're ready for that next step. So now once we're looking at this, and then all it is now is that we take all the points from the very preceding step right here. So after the first transformation step, we're going to take all of those points currently, but we're going to add a -3. Okay, I'm going to underline this. We're going to add a -3 to every value according to that advice I've had earlier in the earlier lecture right there. Or in other words, so adding a -3 is in another way of seeing that means the graph is going to be moved. The graph is going to be moved 3 units to the left hand side. Okay, this same exact graph right here. After we already have done some scaling on that horizontally. Okay. And in this way right here, I was expecting a stretch, right? We flipped and then we stretched the graph. And then once we're done with that, we're going to take that stretched version, okay, move it to the left-hand side by 3 units. All right, and so now let's get it done. So the first point here, 6 comma 3, but I'm going to now add 3. All right, add -3 to every value, to every x value. So now 6 add -3, I'm looking at 3 comma 3. So the first point is transformed into 3 comma 3. The next point at 2 comma 1, I am going to add -3 to this x value. So that gives me now -1 comma 1. That's what this point 2 comma 1 is transforming to. Okay, and then the next point here, -2 comma 3, I am going to add -3 to that. So that now gives me negative 5, comma 3. So that's what this point transformed into. All right, and then this next point right here at negative 10, comma 1 initially, I mean before the moving, before the shifting. Now I'm going to add negative 3 to this x value, giving me negative 13, and then comma 1. All right, nothing is done with any of these y values at all. All right, so now let's continue to finishing out the rest of it. So now negative 16, comma 6 is now transformed into, so from where this negative 16, it's going to become negative 19, comma 6. And then the last one here is negative 25, comma 1. But at this point, this is where we have completed our transformation. This final column right here indicates we had 2 steps of transformations. Okay, we had 2 steps of transformation. So now in that way, this column right here is ready to be plotted on the graph, ready to be, any of these points ready to be placed on the graph, and that's where we call it. It's the guiding points of all of the parent, I mean the descendant function. All right, so let's see now how we can put that on the graph right there. Now in my graphing screen right here, in complete full screen view, let me now put the actual guiding points back again on this parent function in red ink right here, in the red color. And so now, and allow me to move the graphing window a little bit this way, so that I will, because I'm expecting the descendant function is going to be mostly on this side right here, and I'm going to, for better purpose, I'm going to also scale that, I mean zoom it out a little further. All right, so now with that, now we're seeing our transform points right here. These are the points with the descendants function. Okay, but the screen here is still too limited that it's not showing enough all of the guiding points for on the transform function, on the descendant function. So I am going to zoom it out even further. Okay, and it still didn't show enough, and we start seeing some more points being out here. All right, and so now allow me to adjust the setting a little bit so that we can see all the grids. Okay, I'm going to put the grids in finer line right there so that we can see more of the grids and the complete view of the graph. So this last point right here, okay, is the point where it reflected negative 25, comma 1. So these are the complete set of guiding points on our descendant function. Okay, and so now we're gonna once again think about it this way. The original graph in that picture is still showing the original graph. From the left to the right, it started out with the bottom half of a circle, and then it zigzagged down. Okay, it's zigzagging down, and then it's going up and going down. So just that being the fundamental shape. But now for this problem right here, we had a flip. We had a flipped horizontally. So I'm expecting that from the left to the right, things gonna go opposite way. So that zigzag going up, going down has to happen first, and that's what will happen among these points right here. All right, and then another line connecting here, and then these 3 points is going to make up that part where we're looking at the bottom half of a bowl right there. Okay, so now in that way, let's get into the complete full screen view. All right, so now I am going to make an attempt to draw this graph. All right, so let's now draw that graph. So the first thing now, I am going to connect these 2 points as a straight line, just like how it appears here on the opposite end, going backward right here. Then it's straight line between from this far right to that point right there. So now from the far left to this point, I'm going to go a straight line. All right, so just like that. And then from between here to here, it's another straight line. All right, just like that. And then from here to here, just like that. The opposite way is from this far right point back to that, it's another straight line connecting the 2 points. And so now I'm getting that as a hand sketch. Now I'm trying my best. And of course, if we really are doing this, with paper and pencil, then this bottom bow part right here, this bottom half of the bow right here, we can just make the best that we can. It doesn't have to be precisely on nice scale like this machine can give us. But that's now how we have done our graph. our graph for this function g of x, that is that came out as f of minus 1/2 x minus 3/2. All right. And now with that same graph right there, let's use that for an FYT. So I want anyone learning from this video lesson to give it a try on your own. So that same graph reflecting the function right there. All right. So this time, as an FYT for your own trying, I want you to try, anyone learning from this video, I want you to try g of x equals f of minus 2x minus 4. All right, minus 2x minus 4. Okay, so go ahead and get the problem done. You have seen enough details and explanation throughout the entire example here. Now it's time I want you to apply your own understanding into this own problem. So go ahead and pause the video, take as much time as you can. Okay, and then in the end, at the end, I will just simply show the final graph of this the descendant function g of x. All right, so now assuming you have already spent some time pausing the video to get yourself worked on. So here's the graph. So in complete full screen view, again, this is the graph of our parent function f of x. Now these are the guiding points for our graph. Okay, these are the guiding point for our graph in g of x. Okay, and then as we are sketching through the graph, then this is what it looks like. That is our final graph for g of x in blue color right there. All right, and now we are ready for heading into another class of problems. And let's call it now example 4 in our current lecture here. And we are still continuing to do our work on combining all of the horizontal transformations. So we have 2 elementary horizontal transformations that we've learned previously in the earlier lecture, and now we've learned in this particular lesson how we can do a transformation that was a combination of the 2 elementary transformations. Okay, and so now let's look at example 4 here. All right, so in example 4, here's the worded instruction of example 4. We want to sketch the graph of the given function. All right, sketch the graph of the given function by recognizing it as a transformation. All right. Of a known function. All right, so just like that again, of a known function. So we have seen this similar kind of example quite often before, even in earlier the lecture and earlier examples of this current lecture over here. Okay, and so we want to build our skills around these. So the idea now is that for any of the function, we want to just simply recognize the function that we will be sketching as a transformation, okay, of a known function. All right, so there are a couple of those terms that I highlighted that hopefully clicked your attention, grabbed your attention. Okay, so but let me now write down the function. So the first function I want to introduce, let's learn to sketch. Let's sketch. So I mean sketch by hand sketch version. And so now g of x here is going to be, how about square root of minus 2x plus 5. Okay, square root of minus 2x plus 5. So we want to sketch this function by hand. Okay, so the number one thing we want to stay away from, just like any of the earlier examples we have seen throughout the earlier lectures, we don't want to construct from scratch the table of values. Hey, when x equals 0, y equals this. When x equals 1, y equals that. And x equals 2, y equals that. That's the table of value, and we don't want that to happen. We don't want to use that kind of approach because it's going to take a lot of time for us. Okay, and so the worst thing is to throw this into a calculator and get it graphed for us, and then copy and paste that graph, redraw that graph on the paper. That's not how we learn, because we won't see any transformation. So now the point here is that we want to sketch, but sketch with some smart understanding. Okay, so I want to recognize this function as, is this at any possibility a transformation from a known function? That's the thing we put in mind right there to ask about this function. And then once we recognize that this function came out as a transformation from a known function, or in other words, from a parent function, or you can think of this as the descendant function. Is this the descendant function from some other parent function, from other known parent function? Then we're going to apply the recognized transformations. Do expect that there are going to be multiple steps, okay, of transformations involved here now. Okay, so that's what we want to sketch. We sketch, and so the skill that you've learned in the earlier example is the essential skill that builds your skills once you recognize the transformations that are involved in here. Okay, and so now here's how my thought process leads me. Well, looking at this function from scratch, all I see here is the square root. Yes, admittedly, there are a lot of things involved inside of the square root. There are a lot of things involved inside of the square root. Okay? But at least I see the square root. That will immediately remind me of this following known function. And so we don't have to immediately. So all I'm saying, see, all we need is just think of a known function. And then at this point, when I'm about to point out this known function, I did not even point out any connection, any relationship between this g and the known function yet. Okay? The only thing I know is that, hey, we have seen f of x equals square root of x. And I'm saying that this is known simply because, yes, it was one among the toolkit functions that we have learned from earlier lectures. Okay, so in that way, so now once we recognize this known function, tentatively the idea now tentatively is that we want to see this as the parent function. Okay, so if we recognize this as a known function, we want to treat, that's why, like I said, we right now the goal is we want to see this as the parent function, and we want to start making that connection of how g can come out as a descendant function from this parent function. That's the part right there. Okay, and so now in this way, here's how I see it. The square root in our function g right here. The square root in our function g is a square root and then of a minus 2x plus 5. So I'm seeing that it's almost the same, except for f of x, for f of x here, it's a just square root of a simple x. But here, inside the square root, instead of this x, see, put the two things side by side right here, you can see that they're both having square root. But then instead of having this x right here as a simple input, we're having a linear expression being inside of the square root right there. So this linear expression right here inside of the square root, in another way of seeing it, I see that as so the point now is that square root means we're looking at the rule of f. Okay? Square root means we're looking at the rule of f, because just f here, anytime we're looking at this rule of f, because we recognize that the known function here is the function f. So f here represents the rule of taking the square root of whatever. I mean really meant whatever, because now inside of this square root in our g function, it has minus 2x plus 5 inside of it. So that's why, hey, wait a minute, does that mean f of minus 2x plus 5. And yes, that's what it is. Because again, just simply f means the rule is to take square root of whatever. So now that whatever here is going to be this linear expression minus 2x plus 5. And so doing that, it will land us exactly into this square root of 2x plus 5. So that's the thought process that's laid down to lead me into this. But hey, wait a minute. This is going to be our g of x. So that's what g of x is. Because we recognize this square root of minus 2x plus 5 inside of it is g of x. So now we've recognized that relationship. G of x here came out as a parent, as a descendant function from its parent, f of minus 2x plus 5. All right. And so now this is the thought process, and this is the final recognized relationship between descendants and its parents. All right. So now, but what transformations are being involved here in this? Now, just like the earlier example, I recognize I am going to factor out this lead coefficient inside of in my linear expression inside of f. So now that becomes minus 2 in parentheses, because this is after factoring out the lead coefficient, which involves a negative sign as well. Okay, which includes a negative sign. So here it's x minus, factoring out a negative sign on the second term right here results in a minus sign, 5/2. All right. And so now I know that this 2 right here will cause for us as an expectation, we will have this is responsible for horizontal scaling. Okay. That's teared all down. And this horizontal scaling may or may not, and in this case it will have a negative, it has a negative sign, so it will have a flipped due to that negative sign. Okay, and then this value right here is indicating that 5/2 right here, and we already had this in x subtract, so that means that it's going to have some sideways shifting. Okay, so now this is going to have a horizontal, horizontal shift. All right, that's how I see it. Okay, so now we are ready. So the last thing before I move to the other board, I'm moving to the other board for getting it down, let's look at the graph of this known function. Okay, so all right, so on my graphing space right here, this is the graph of the famous known square root function. All right, that square root function is here. And it has famously a few guiding points here. Now I can also go ahead and put labels in that, numerical labels in that. So this is the graph of the guiding points. The graph of the square root function, that known square root function, quite famously known. Okay? And we've learned this from the toolkit functions. And so now on this board of mine, let's now go ahead and sketch that function for g of x. Let's sketch that as a transformation. So the first thing I'm about to do, I'm going to build that table. Okay, that table of the guiding points. So I already showed the guiding point. I already displayed the guiding point on our original parent function. And we're still seeing that here with the graph. So now again, g of x is recognized as f of minus 2, but in parentheses x minus 5/2. Okay, and so let's now build that table. All right, so one column, the very first column of our table is going to list all the guiding points on the original parent function. So the first point I spotted on the graph right there is a 0, 0. Okay, the next point here is 1, 1. All right, the next point down is 4, 2, and the next point further out is 9, 3. So these are, and so again, the idea of the guiding point is just any of those points where it stays right on the grid, and they are useful for defining the shape of the graph. That's all it matters. Okay, that's all it matters really. So now I am going to make the sketch for I'm gonna nail down the guiding points after our first transformation. Okay, and so the first transformation is going to be f of minus 2x. Okay, f of minus 2x. So it's that f of ax form. And so now we've done this quite often at this point. All it is now is we're going to multiply every x value of the graph. So here we're going to just apply that understanding. We're going to multiply every x value on this list of guiding points right here by 1 over a. Multiply every x value by 1 over a. A in our case here is negative 2. And so 1 over a is going to be 1 over negative 2. Or in other words, it's a negative 1/2. This is 1 over a. We're going to multiply every x value. Okay, so the x values on these guiding points are no exception. We're going to multiply all of these x values by 1 over negative 1 over 2. Okay, so now I'm looking at the next point here. The transform point is a 0, 0. Simply just that, because 0 for x here multiplied with negative 1/2, that gives me 0. The y value stays exactly the same. This next point here is 1, 1. Now it's transformed to negative 1/2, 1. Because again, the x value was multiplied by negative 1/2. Okay. Now 4, 2 is now transformed to negative 2, 2. Y value stayed the same. X value was multiplied with negative 1/2. And that's the reason why 4 times negative 1/2 gives me a negative 2. Okay. And then for the next point, 9, 3 is now transformed to negative 9/2, which is a negative 4.5 if anyone is thinking numerically as a decimal. And then 3. Y value again stayed the same. X value became negative 9 over 2 simply because 9 multiplied with negative 1/2 and gave us this point. Okay, but this is the end of our first step, the end of our step 1 transformation. This is f of minus 2x. Okay, but that's not quite our function g of x. So g of x is f of minus 2 times, but not x, times x minus 5/2. So now we're in that form again. X subtract, that means it tells us clearly that clue that we're going to expect some horizontal shifting. But in this case, we're going to shift by the positive amount of 5/2. Okay, so now let me write it down. So f of minus 2, okay, in parentheses, x minus 5/2. So this 5/2 here is a positive quantity. That means we are going to shift. We're going to move our currently transformed graph here. We're going to move it further to the right-hand side. By how far? By 5/2 square grids. Okay, 5/2 of the square grid. But so see, saying that description out it is easy. Okay, but visually, it can be hard for someone to visually imagine it. Okay, so now let's just let's just stay with that advice. I'm simply going to add 5/2 to every x values here from the very preceding step like that. So from this preceding step, I'm going to add 5/2 because it's positive. Aside from that x subtract right here, 5/2 is positive. So we're adding 5/2 to every x value. Okay, so now, so that's why this first point from the preceding step, it was 0, 0. Now it's 5/2, 0. That is simply because the 0 plus 5/2 gives me a 5/2. That 0. And now for the next one, the next point right here, negative 1/2, 1. Now it's transformed into 2, 1. Okay, and that's simply because a negative 1/2 plus a 5/2 is a 4/2, and that reduces down to a 2 right there. So that's what this point is transforming to. Again, nothing happened to the y value throughout these problems. Minus 2, 2 is now transformed to positive 1/2, 2. And that's, again, y value stay the same. We had 1/2 here because minus 2 plus the 5/2 gives us positive 1/2. Okay, and the last point right here, negative 9/2, 3. Now it's transformed to negative 2, 3. Okay, y value stay the same. this minus 2 came out because negative 9 halves added with positive 5 halves like that. Okay, and that gives me a negative 4 halves, which reduces down to a negative 2. So now this is the final list of the guiding points. And these are the guiding points of the final transformed g of x. Okay, so now we are so ready to put that on the actual graph like that. All right. So now with the graph of our original parent function. Okay. Let's now show the guiding points that reflect the transformation. So now just as an expectation, just as expected, comparing these guiding points on G, and we already had all the guiding points listed here with proper values listed. We can double check for consistency in our calculation with those points. Okay, and now by looking at those points right here, we already noticed the graph is forming into a shape that's going opposite way with the current graph in red, with the parent graph in red. And that's what it is, because we had a negative a here, which in our expectation we already expected that there would be a flip, a horizontal flip. Okay, so in that way now with my graph currently presented, that's expected that we are looking at these guiding points going in the opposite way. So now let's throw in the actual graph. All right, so with the actual graph, now I'm going to draw, but when we actually sketch, we sketch always from the left to the right by connecting these, but we're going to connect these from in a curvy way right here. Okay, in a curved shape. So now this is how it's going to sketch. All right, and that's how our graph, okay, that's the graph for our g of x function right here, being this function right here is the f of minus 2x plus 5, okay, f of minus 2x plus 5, or in other words, g of x equals square root of minus 2x plus 5. This is the graph for that in blue. All right. All right, so in this same class of problems, let's look at part B of our example 4 here. Okay, and so let's now look at how about g of x being absolute value of 1/2 x plus 1. Okay, absolute value of 1/2 x plus 1. And so, and again, we want to sketch this function, but instead of using paper and pencil and draw a table of input and outputs, we don't want to do that. We definitely don't want to just simply punch this into a graphing calculator and get it done and then copy that on paper. That's not what we want to do, because we learn nothing about the transformation. Okay, the more we try in that direction about recognizing it as transformation, the better we will get, the more fluent we will get with these transformation steps right here. So we want to recognize this as some possible descendants from a parent's known function. Okay, so let's recognize a known function. So just simply from very scratch right here, from a very scratch ground up level, I only see absolute value. So disregarding all of that fancy things going on inside the absolute value, I recognize that we have already seen the following function. The rule can go as basic as whatever function we call it f, okay? The rule says take the absolute value of whatever input, okay? The rule says take the absolute value of the whatever input. And so now this function here is known. It's known since the lecture that we were looking at, or at least investigating the toolkit functions, okay? And so now, and that's all I'm saying. You know, it's known just in a sense that we're seeing some absolute value. So that thought came through my mind that, hey, let's look at this known function, f of x equals absolute value of x. And so now once we pinpoint this known function, we want to see how this can be a parent we want to recognize even further the relationship, the descendants parent relationship between G and F. Okay, and so in that way, now I'm gonna sketch down my thought process again. Now the rule of F here from this function says, the rule of F here says whatever input. That's why I'm leaving it empty here, because it's really ready for any input. Whatever inputs for F, the rule of F says we're gonna take absolute value. Whatever input, we're gonna take absolute value. That's the rule for this absolute value function. And so in this way now, so think about that. If we're gonna step even one more step further, so what if we substitute in the inputs minus 2x, I mean 1/2 x plus 1. If we're substituting in that linear expression as the input for f of x, then we definitely will produce the following result. And especially we have already done that kind of problem where we had some advanced evaluation problems on a function. And so now I can just simply take the whole linear expression here as is, 1/2 x plus 1, and I'm going to put it all, package it all inside of my absolute value symbol. Okay, so then wait a minute. We recognize that this is actually indeed now that absolute value of all that 1/2 x plus 1 is now actually g of x. So that's now how I point out. So I recognize that this is g of x. Okay, and so in that way, now I see that g of x is related with this f of x here. So now we can legally say f of x is the parent function, but it's f of 1/2 x plus 1. That's how I see the relationship between g of x and f of x. Okay, that's how we got it set up. And so now once we recognize all of that property, okay, then we are ready for getting the transformation done right here. And so one further step I would like to point out. So now it's a linear expression clearly, but we want to see this. We want to factor out that linear coefficient, in front of the linear term right here, so that we can see the transformation steps even more clearly. So this is indeed, and allow me to write it a little further out so that I can have more space here. So how about so g of x here is f of 1/2 x plus 1, but that means this is going to be f of, so now in the brackets right here, factoring out 1/2 is going to give me, and this leading coefficient itself was already positive, so factoring out the leading coefficient will not change the sign. So now I'm looking at x plus 2. Okay, but now be careful a little bit with that plus 2 right here. This plus 2 is indicating that we're looking at, really it's minus a -2. Okay, minus -2. All right, so now with all of that, we are ready, because I need to see this x plus 2 as x subtract -2, so that x subtract will ring up that bell about we are going to have a horizontal shifting. It's a good sign about horizontal shifting. And then depending on whatever the remaining sign of that value right here, that will tell us visually where the graph is going. Is that going right or going left? Okay, but now we have all of that information. So needless to say, yes, this 1/2 here is responsible for horizontal, okay, horizontal scaling. All right, and then this right here is responsible for horizontal shifts. All right, that's the expectation. So we are expecting 2 elementary transformations being applied here. All right, so now let's bring up the actual graph of this, okay, on the board. All right, so now in my graphing space right here, this is the function, this is the graph of the parent function. All right, this is the graph for absolute value of x, and it has a few guiding points here. That's a few recognizable, very recognized guiding points, easily right on the grid. So the corner right here itself forms a 90-degree angle, and each line here is a 45 degrees line away from the origin. Okay, And so these are the points those are the points right on the grid that define our shape. It's a V shape, famously. Okay. And so now we want to see how that shape will be transformed according to this rule over here. So it's f of 1/2 times in parentheses x plus 2. Okay. All right. So now I'm going to advance to the other board to get the work completed. All right, so now I'm going to repeat that. I'm going to repeat what we had earlier a little bit. So g of x here is already known to be f of 1/2 times x minus -2. Okay. So we have a horizontal scaling. We have a horizontal shifting. Okay, all of that is being indicated here. All right, so and this is our a value. Okay, this is the a value. So a here is 1/2. All right, a there is 1/2. So now let's construct a table of values, and we're going to apply we're going to construct a table that contains all the guiding points, not the table of values, the table of all the guiding points. Okay, and so f of x. In the parent function, it has the following guiding points here: -2, 2. Okay, and then we have -1, 1. We had another point right at 0, 0. And we have another point at 1, 1. And we have a point at 2, 2. All right, so these are the guiding points on the original parent function. And so now let's look at the transform point after applying the first transformation step. So now how about f of 1/2 x? And so as I said earlier, with this form right here, f of ax, this a is already indicated as being of 1/2. So that means we're going to have, now the a value here is a positive value, so no horizontal flip expected here. Okay. And then, since the absolute value of 1/2 is less than 1, clearly, then we're going to expect a horizontal stretch. It's going to be wider, okay? But like I said, all of that, the visual description that I'm saying through the mouth, it's easy, but it's only easy for the people who are fluent with looking at things, who have good sense about visualization. But for a larger majority, not everybody is really that visual. Okay, not everybody is seeing things that visually. Okay, and so the easier advice now, we're gonna multiply 1 over a. Multiply 1 over a. So 1 over a in this problem. 1 over a in this problem really is 1 over 1/2. Okay, be careful with the fraction right there. So we're gonna multiply every x value by 1 over a. But 1 over a is 1 over 1/2, which is a 2, a positive 2. So now that means I am going to multiply every x value from my parent function with 2, with 1 over a. Okay, and so now these guiding points are no exception. So now this is how the first points get transformed into. -2, 2 is now transformed to -4, 2. Y value stay the same. -4 came out because x value is multiplied with 1 over a, which was 2. That's how -2 times 2 is -4. All right, and so now in that way, again, -1, 1 is transforming to -2, 1. Y value stayed the same. X value here came out because -1 times 2. Okay. Next point, 0, 0 is transformed to 0, 0. Y value really stayed the same. X value here looked like it stayed the same, but simply because 0 times 2 also equals 0. Okay. And now we're going to advance to the next one. 1, 1 is transformed to 2, 1. All right, 1, 1 is transformed to 2, 1. Y value stays the same. Okay, but x value became 2 simply because 1 times 1 over a, which was 2. equal to. Okay, and then the last point here is 4, 2. And now you already had a clear understanding of why it's like that. Okay, and so now these are the guiding points after transforming the function by transform g from f of x to f of 1/2 x. But this is not the complete g of x yet. Okay, this is just f of 1/2 x. We transform by multiplying every x value here with 2. Okay, and so now I'm going to move on to the next step. So the next step here is going to get us to the final. The next step here is going to get us to the final g of x, the final transformation. So f of so how about 1/2? But instead of x now it's x minus -2. Okay, x minus -2. So now that x, subtract that x minus right here is indicating clearly that we have a horizontal shift left, shift right. And this is indicating for us we're going to shift left because of that -2. Okay, but once again, as I'm saying out loud that visual description, it's easy for somebody to catch, but it's not easy for a larger group of people to catch that. It's not, and practically when we get to moving it left and right, it's hard to land them into precise value. So a real crystal clear, the advice is here. We add every x value with -2. Okay, we add -2, we add this value to every x value. Okay, we add -2 to every x value. So now we have a solid way to put our points right on the spot. So now -4, 2 becomes, is transformed to -6, 2. -6, 2. Okay, y value stay the same. -4 became -6 because x value added with -2. Okay, and so now I'm advancing to the next point right here. -1, 1 now is transformed to -4, 1. Again, y value stayed the same. X value came out because -2 added with another -2, producing -4. Okay, and now the next one right here, 0, 0, is now transformed to -2, 0. -2, 0. And that happened because, once again, y value stayed the same, but x value came out because x value here became -2 because 0 plus -2. Okay, plus a -2. And then so now in that way where you already caught that direction of where I'm going, the next point here becomes 0, 1. And then this next point here is 2, 2. All right. So once again, that 0 came out because 2 add with -2, giving 0. 4 add with a -2, giving a +2. All of the y values stay the same. Okay, so now this is this final column right here has all of our final guiding points on the blue graph right there, on the blue graph. All right, so now we are ready to put all of these final points right here on the actual picture. So let's plot it on. Okay. And so now on our graphing space right here with really close zoom, like in full screen view. All right, so let's have a look at the guiding points, the final transform guiding points. Okay, so here they are. So we had 6 guiding points from the original parent function. Okay, now let me hide these away a little bit. So these were the 6 original guiding points on the parent function with labels along with them. Okay, and now we have these are the final transform guiding points right here. And it looks like, so from the left to the right, it's still showing that V nature right there. Okay, see, if we think about, if we imagine that we're sketching through and trying to draw a line through connecting these points, it's gonna form into a V shape. So it's already telling a story. And then we can just quickly double check with our calculation on the board here to make sure our calculation goes consistent with those points being placed by machines right there. Okay. And so now putting all of those points, right, and we can think about if we're sketching that, and this is the immediately the next step right after getting the the transform points down right here. So we put the transform points down, right, with coordinates already calculated from the table, and these are the coordinates. And now we're gonna just simply connect the graph. Okay. All right. So now connecting the graph. This is what happens. Okay. So it's a straight line down, just like that piece of the graph. We had no horizontal flip, so it's gonna happen just like that, but it's gonna be more widely spread it out right there. Okay. And then we're gonna connect again with these points. All right, so the graph now in blue is the graph of g of x equals absolute value of 1/2 x plus 1. All right, and before I finish and leave this example, let's do another FYT right there. Okay, so I'm going to have an FYT for everyone learning from this video lesson. All right, so as far as an FYT, let's have a look at, okay, how about g of x equals all right, so as far as the g of x, as far as an FYT, I want you to sketch the graph of g of x here being 2x minus 1 in parentheses squared. Okay, I want you to now get this one done. Okay, but sketching it not by constructing table of values, not by directly throwing it into a graphing calculator, but I want you to sketch this by recognizing some known function that's related to this. And then by seeing this g of x as a transformation from that known function you recognize. All right, so go ahead and take your time. This is an FYT, so I will only be showing. So once you resume with this video, after pausing it to make your own try right there, once you resume it, I will show that known function. And the known function I have may also not look exactly like yours right there, but these are standard enough, so eventually instructor and student will click into the one same known function. Okay, so I will tell what known function that I recognize, and then I will tell you how this graph is a transformation of that known function. Okay, so go ahead and pause the video. All right, so now hopefully you have spent enough time working after you pause the video. So now that known function I recognize is f of x equals x squared, and this is again among the list of the toolkit functions. Okay, and so now I'll just swing over to the graphing space. All right, so this is the graph of the known function f of x, and so tentatively I see this as a parent function. Okay, and these are now my guiding points on this parabola of the parent function. The guiding points on the transform g of x will be these blue points. Okay, and then you can compare with your own work. And now, as we sketch through these points right here, the graph will look as following. And this graph in blue now is the graph for g of x.